Hello everyone. In this video, I would like to talk about part 1 of the Fundamental Theorem of Calculus. So what I would like to do is just give you a brief overview of what part 1 says, and then I want to show you how to use part 1 of the Fundamental Theorem of Calculus in a specific example. So to begin with, when we're looking at the Fundamental Theorem of Calculus part 1, we need a function f that is continuous on a closed interval from a to b. So we have a function f that is continuous on an interval from a to b. And if all of that is true, that means I can find the integral of this function. So we can take a look at the integral from a to b of the function f of x dx. So because we're saying that f has to be continuous, I know that this integral has to exist. Well, now let's say we want to rewrite that a little bit. So let's pick out a number x within our interval a to b. And let's take a look at the integral from a to that number x. Well, now x, I can't use f of x here, so I'm going to do f of t dt. So rewriting this a little bit, now I'm going from a to another x value that is within that interval from a to b. This is a function that depends on x. So as that x value changes within that interval from a to b, the value of this integral also changes. So because this can be thought of as a function of x, let's write capital F of x is equal to that integral. So that's the setup for part 1. And now we're going to continue on by saying that we want to find the derivative of capital F of x. So I want to find the derivative of this function. So in other words, we're going to do d over dx of this integral that we just defined earlier. So the integral from a to x of f of t dt. So essentially what I'm doing is I'm finding this integral of the function f of t. T in this case, that is basically a dummy variable. It could be anything because this is going to depend on where x is. So we find the integral, x will go into that integral at some point, but then we're going to take the derivative of that after we find the integral. What part 1 of the Fundamental Theorem of Calculus gives us is that if I find this derivative of capital F of x, what I end up with is f of x. So taking a look, these two operations, the derivative and the integral, they basically undo each other. So if I take the integral and then take the derivative, I end up right back where I started. Also taking a look at this final result we have f prime of x is equal to f of x. Another way I can think about that is if I take the derivative of capital F and I end up with lowercase f of x, that means going the other direction, capital F of x has to be an antiderivative of f of x. So that's how these are related to each other. Taking the integral of something is very much similar to finding the antiderivative. Let's just start here with a very simple example. So let's say we have a function g of x, and let's say that this function is an integral from 0 to x of the square root of 1 plus t squared dt. Again, within here, the variable t is what we call a dummy variable. It could be anything because after I find this integral, like I said earlier, x would go into that somewhere, and it's a function that depends on x, not t. All right, so now let's find the derivative of g of x. So I want to find the derivative of this integral. So the integral from 0 to x of 1 plus t squared all over dt. So using part 1 of the Fundamental Theorem of Calculus, the derivative basically undoes the integral, and what I end up with is a function in terms of x. So here I'm just going to replace t with x, and that's what we end up with. So that's the very straightforward way. I have a constant as the lower end of my interval for the integral, and then the upper bound here is the variable x. Taking the derivative of the integral, they basically undo each other, and I'm replacing that variable with x. Now, let's take a look at an example that's a little bit more complicated. Okay, so here's my example. I have d over dx of the integral from x cubed to 5, and then on the inside we have t to the 4th plus 1. That is all raised to the 1/3 power, and then we have the dt in the back as well. So there's a couple things that we need to note right away about this. The first one is my lower bound is the variable x cubed, and then the upper bound is my constant. If I want to be able to use part 1 of the Fundamental Theorem of Calculus, my variable has to be the upper bound. So we need to use one of our properties of integrals, where if I do the opposite of the integral, I can switch the upper and the lower bounds. So I'm going to do the opposite of this integral, and I'm going to move that negative just out front. So negative d over dx, and then here we're going to have the integral from 5 to x cubed. And everything on the inside will stay as is, so t to the 4th plus 1 to the 1/3 power, and then dt. Now, the second thing that we need to note about this example is my upper bound here now is x cubed. It is not just a plain old x to the 1st. So just to explain this a little more, we are taking the derivative of this entire thing. This is a function of x. It's written as an integral, but it still is a function. And I'm still taking the derivative of it. And because that's not just a plain old x to the 1st, when I take the derivative, I actually need to apply the chain rule. So I'm going to write everything out here the way that we've seen the chain rule before, but just to give you an idea what's happening. So I'm going to define y as this integral from 5 to x cubed. So the integral from 5 to x cubed of t to the 4th plus 1, and then to the 1/3 power, and then dt. And then I'm also going to say let u equal x cubed. So I still want to find the derivative of this whole thing, but I define this as y. So what I want to do, still have my negative out front, I want to find dy over dx. And if we split that up using the chain rule, we have dy over du times du over dx. So we have our two parts here. And let's find the derivative of each of those. So I just need to make sure this negative keeps following down. But I'm going to take the derivative with respect to u of this integral. So from 5, and now instead of x cubed, I'm going to let that be u. And then we have t to the 4th plus 1 to the 1/3 power, and then times dt. And then we also want to find the derivative with respect to x of u. So the derivative with respect to x of x cubed. So that's applying the chain rule. Now let's keep going. The first piece here, what I have all in brackets, I'm going to take the derivative of that. This is part 1 of the Fundamental Theorem of Calculus. So if I take the derivative of an integral, basically they undo each other, and then I can just plug in this variable instead of t. So I still have my negative sign, and then I'm going to have u to the 4th plus 1 to the 1/3 power. The dt goes away now. And then we're also going to have the derivative of x cubed with respect to x. So using the power rule, that is 3x squared. Now to finish up, we just need to replace u with our variable x again. So substituting in x cubed, where we have an x to the 4th, a u to the 4th. So we're going to have x cubed to the 4th. That's the same as x to the 12th plus 1 to the 1/3 power, and times our 3x squared. And why don't I just rewrite this a little bit? So I'll come up here. So our final answer, the derivative of this entire integral, is going to be negative 3x squared times x to the 12th plus 1 to the 1/3 power. So because we are taking the derivative of something, and because my x variable is not just x to the first, I do need to apply the chain rule. So essentially we use the first part of the fundamental theorem of calculus, and we're also using the chain rule to get our final answer.